Hey everybody, welcome back. I've got a really nice infinite series for you. So we want to find the exact sum of this. This is the series from n equals 1 to infinity of arc cotangent of n squared plus 3/4. And in order to get our hands on the sum, we're going to need some tools to help us out here. So first of all, property 1 we proved on the channel. This is arctan of x minus arctan of y equals exactly this. Now, for property 2, we haven't proved this exactly, but we proved something very, very similar. So you could do this as an exercise. Just be careful for which x's this is true. So be careful of that. For number 3, we want to just recall that the sum of a series is the limit as n goes to infinity of the nth partial sum. And we're going to need lots of clever algebra here. So that's going to help us out as well. So we'll be on the lookout for this. So we're going to start this problem, and the first thing we're going to do is use property 2, so be on the lookout for that. And so here we go. Okay, so by property 2, we've got the following. So this is the series from n equals 1 to infinity of the arctangent of 1 over n squared plus 3/4. So that seems pretty nice. So now we want to think about, well, how can we do some algebra so we can use property 1, right? So I mean, I've got an arctan. That seems maybe nice, potentially, but it's all going to be about, can I get this into this form with some algebra? If we're kind of clever, we can think about this in the right way, or at least a helpful way. So let's think about this in the following way. So this is the series from n equals 1 to infinity of the arctangent of 1 over. Now, 3/4, I can think about 3/4 as 1 minus a quarter. Let's see why that's helpful. So there's the minus a quarter plus 1. And that might be nice because that's actually the difference of perfect squares. We can factor that, and that will help us get that x times y that we're looking for. So let's go ahead and do that. So let's rewrite this, and then we'll factor this portion. And when I rewrite this, let's rewrite it so this 1 is first, just so it looks like property 1 or formula 1 from the tool sheet. Okay, so again, that 1, we're going to write that right here. And then again, we're just going to factor this as the difference of perfect squares. So that'll factor into n plus a half times its conjugate, n minus 1/2. Okay, so that seems pretty nice so far. Okay, so in terms of property 1, I've got the denominator all set. So that seems pretty nice. And the question is, can I rewrite this 1 here in such a way that I have this? Well, it turns out we can, because let's just do a little side observation. So let's observe the following, right? So 1, in particular this one, is equal to n plus a half minus n plus a half. But that's exactly n plus a half minus n minus 1/2. But that's perfect, right? Because this is, we can think about this as the x from the formula, and this is the y. So that'll give us the x minus y. It's still equal to 1, so it's nice and legal. And let's go with that. So that gives us the following. So we've got the series from n equals 1 to infinity of the arctangent of, now we said n plus a half minus n minus 1/2. Again, that's still 1, but super useful. Okay, and downstairs we have the following. So this is 1 plus n plus a half times, again, the conjugate n minus 1/2. And that's going to allow us to use that formula, right? So we can now turn the right side, we have essentially this, right? And we want to turn that into this. And that could be pretty nice. Okay, so by our formula here, so we've got the series from n equals 1 to infinity of the arctan of x. Well, what's playing the role of x is exactly this. So that's the arctan of n plus 1/2 minus, from the formula, the arctan of y. And again, playing the role of y is n minus 1/2. So that's the arctangent of n minus 1/2. And so now we want to see if we could treat this as maybe a telescoping series. So we're going to investigate S sub n, right, the nth partial sum, and then we hope that some of the middle terms will cancel, and then we'll take the limit at the end to get the sum. Okay, so this seems pretty nice. So our next goal is to investigate S sub n. Okay, so let's observe that S sub n is equal to, so again, yeah, the sum of the first n terms. So we're going to start off by plugging in 1. I did the same thing I did last video. So remember the last time I did a telescoping series involving arctangent? I said, I'm laughing at myself. So last time I said, okay, now I truly appreciate this notation just in terms of writing things more efficiently. Well, I'm back to old arctan. So again, let's commit. So here we go. So plugging in 1, we've got arctan of 1 plus a half, that's just 3 halves, minus the arctan of 1 minus a half. So that's just a half. Plus, and then we'll plug in 2. Right? So if we plug in 2, that's going to be the arctan arctan of 2 plus a half. So that should be the arctan of 5 halves, right? So arctan of 5 halves. So that seems pretty nice. Happy with that. Minus, again, if I plug in 2, so 2 minus a half is 3 halves, right? So this is the arctan of 3 halves. So this seems super promising, right? Because I've got this situation where things might cancel. Let's get some more terms so we can see it more clearly. So we're going to plug in 3. So this will give us the arctan of, let's see here, 3 plus a half here. So that should be 7 halves. So that's the arctan of 7 halves. Minus, now if I plug in 3 here, so 3 minus a half should be 5 halves, right? So this gives me the arctan of 5 halves. Okay, so I'm excited about that. Some canceling here. Some canceling here. What the heck? Let's go ahead and plug in 4. So that gives me the arctan. Looks like 9 halves. Minus the arctan of 7 halves. Okay, and then we're going to say plus dot, dot, dot. So imagine we have all those middle terms. And then the term before the nth term, the n minus first term, would look like this. So this would be, again, the term before the nth term. So this would be the arctan of n minus 1 half minus the arctan of n minus 3 halves. So again, that's the n minus first term. And then plus, and then the nth term looks like this. So that's the arctan of n plus a half minus, can we fit that? I think we can. So that's the arctan of n minus a half. There we go. Okay, so let's see what's going to cancel and what's going to stay. So this will clearly cancel, right, with this. But I don't think there's an opportunity for this to cancel. So this will definitely stick around. This will cancel with this. This will cancel with this, etc. Now this will cancel with this. This would cancel before it somewhere. And so this would stay. So it looks like S sub n collapses down to this. So I'm going to write this as this minus this, just so I don't have a negative on the left. It's fine if you do. It's just a habit. So that's the arctan of n plus a half minus arctan of 1 half. And I think, so at this point, of course, we want to go ahead and take the limit. But then I'm going to show you maybe the sum in 2 different ways. That might be appealing. So we'll do that. Okay, so that's not the sum. We still have to take the limit of S sub n, because that's the sum of the series. And so, so we have the following. So the actual series, the sum of the series, we start with an arc cotangent, right, of n squared plus 3/4. That's equal to the limit of S sub n. So the limit of S sub n Okay, so that seems pretty good. And so if we just think about the graph of arctan, right? So as the inputs get arbitrarily large, the outputs get closer and closer to pi over 2. And that's a constant, so of course the limit of a constant is exactly that constant. Okay, so that's one way I can think of the sum of the series, and that's perfectly fine, right? There's nothing wrong with that. But let's make a couple observations. Again, we can do this in a couple ways here. So let's try the following. So just in terms of rewriting that and maybe getting something that seems a bit cleaner. Okay, so what we can do is, we can consider this limit. And then we just know we've got a difference of arctans, right? Well, we know how to deal with a difference of arctans, right? I think we had property 1, right? So property 1 allows me to rewrite this. So property 1 says, hey, I can rewrite this as this, right? So we can use property 1 right here. So let's go ahead and do that. So by property 1, I can think about this as the limit is n goes to infinity. And again, the point of this is just to get another form for this, just for some fun. So this is the arctangent of x minus y all over 1 plus x times y. Okay, we can clean that up a bit. So that's the limit as n goes to infinity of the arctangent of n over, let's see if we distribute here. So that's going to be 1 plus a quarter. So that's going to be 5 quarters, right? And then that'll be n over 2. And let's see here. So I'm just going to get rid of the fractions, which is fine. So arctan, just multiply the top and the bottom by 4. So that'll be 4n over 2n plus 5. But that's exactly the arctangent of 2. Okay, so that's another way to get the sum, or just a cleaner expression for the sum, I should say, or a different expression for the sum. So now you might be saying, okay, well that's interesting because we have this and we have this. Are they really the same number? Are they actually the same? And what we could do is we could actually use a little bit of Calc 1 to show that these are equal. So this is a fun little extension here. So as an extension, so let me move this up just a little bit here. So we're going on a little bit of a journey here. So extension, show that, what do we say, pi over 2 minus the arctan of 1/2 is equal to the arctan of 2. So bonus math. Okay, so yeah, let's do this using a little bit of Calc 1. I think this will be fun. So let's recall the following. So recall. Let's see here. So say let that interval be a subset of the reals, right? So, and then let's define f from, so if f from I into R has the following property, so let's say given by y equals f of x, has the property that f prime of 0, I'm sorry, f prime of x equals 0 for all x and I, then f of x is constant on I. Okay, well, let's consider something helpful. So let's consider f of x equals arctan of x plus the arctan of 1 over x. And then for x from 0 on. Okay, so let's compute the first derivative. And basically we're going to show that the first derivative is 0, and then we're going to use that to help us prove this. So the first derivative is 1 over 1 plus x squared. And then here, so this will be plus 1 over, now we need to use the chain rule carefully. So this will be 1 over, so it'll be this, the inside squared, times the derivative of the inside. So that'll be 1 over x squared. Now the derivative of this would be, well, negative x to the negative 2, which is negative 1 over x squared. And, well, that's actually pretty nice because that gives me 1 plus x squared, reciprocal, so 1 over 1 plus x squared. And then this will be minus 1 over, and then I distribute, that'll be x squared plus 1, but that's the same thing, so that's 0. And so that tells me that f is constant, right? So f is constant. On 0 infinity. So here's where we get to be kind of clever here. So f of 1 would be equal to, so I'm just doing a computation. So I know for all inputs, right, this is a constant function, so again, we can really use that and be clever. So this would be the arctangent of 1 plus the arctangent of 1 over 1, which is also the arctangent of 1. But we know that the arctangent of 1 is pi over 4, so this is pi over 4 plus pi over 4. And so this is pi over 2. So I know for any input, because this is a constant function, right? So that's actually a constant, it yields the same value for any input, that I can actually consider x equals 2, right? So if I consider f of 2, that's the arctangent of 2. Hopefully you can see why that's helpful, right? Because we're ultimately trying to say something about this, right? So that's pretty helpful. So we've got the arctangent of 2 plus the arctangent of 1/2. And since this is a constant function for any input, it yields the same output. So that's pi over 2. And so then you can see that instantly gives us our result. So pi over 2 minus the arctan of 1/2 equals the arctan of 2. So really cool, nice little bonus math there. So cool, hope you enjoyed that. I really enjoyed that. Sums are super tricky, super interesting, a lot of fun.